Excuse me, sir.
Yes,
Sir, when will you share the Google Form link for the lab components?
I think I already informed to Victoria ma'am. She will share either today.
Okay, sir.
Six. Oh, it is okay. I just tell them to live that. Just give me a second, so I update. Okay. So I informed the support team. Maybe live in within some time. For the week 7, any doubts in practice assignment? Yes, for week 7, any doubt in the practice assignment? No doubt.
We haven't done that yet, sir.
Okay, last day we got 2nd March.
It would be nice if they extend it, sir.
Okay. Any topic you want to discuss related to the week 6 and week 7?
Maybe week 7 we can do some revision kind of,
Okay.
because I haven't started it yet.
Oh. Mm. So basically, the week in the till week 6, we generally discuss about the ideal op. Okay. So in the case of ideal op-amp, what we consider the bandwidth is infinite. Okay, infinite bandwidth op-amp. Okay, that means it will be the response of that particularly operation amplifier is not dependent on any frequency component. So I'm going to share my. No, it is it's not checked yet. Probably I will do that today or tomorrow. Okay, so till week 6, we discussed that op-amp is ideal. What is the meaning of op-amp is ideal? That means if op-amp gain, okay, that is not a function of frequency, not a function of frequency. For any frequency, the operation amplifier gain is remains same, and that particularly gain is maybe 1 plus Rf by R1 or minus Rf by R1 for the non-inverting and for the inverting. Okay, but practically, if we go with the operation amplifier, hmm, this is my circuit.
Sir,
Yeah,
but the transfer functions that we get are frequency dependent, no, sir?
transfer function is a different thing, but if we are talking about the gain,
Okay, sir.
okay, so that gain is basically not dependent on any frequency component. Now, if we are talking about the internal diagram of this operation amplifier, simplified internal diagram of this operation amplifier. Now, this particularly consists with the resistor, okay, and this resistor's value R is also dependent on frequency. It is also a function of frequency. Okay, so similarly, the voltage source, okay, with the respect to the frequency, the value of voltage will be vary. Okay, so not only this one, there are some other components, other particularly parameter factors also there in the operation amplifier on which that particularly value is dependent on the frequency. So that's why if we are talking about the ideal, no frequency dependent, but if we are going with the practical or non-ideal amplifier, okay, so that particularly the gain is a function of frequency. Okay, so if we define that A is omega u by S or S by omega u, okay, that S by omega. So this is a dependent on the frequency, and this omega u is nothing but the cutoff frequency. Okay, cutoff frequency, but this cutoff frequency for open loop. What is the meaning of open loop? When we are talking about the operation amplifier. If we see this particular operation amplifier, okay, so this particular operation amplifier will have a cutoff frequency omega. But if I go with the implementation of this one, so due to this feedback, my cutoff frequency is changed. Cutoff frequency is changed. Okay, so now it is a closed loop system. In the case of closed loop system, my cutoff frequency will be dependent on some other feedback parameter. Okay, also dependent on feedback parameters. Clear? Sometimes it says S by omega u or some S by omega p. No issue with that. Clear?
Yes, sir.
Now with respect to this one, if I talk with the transfer function, so v naught upon vi is nothing but equal to 1 by f into af upon 1 plus af. Now this gain is now s by omega u. Gain is s by omega u or s by omega p, or sometimes it is called the a upon 1 plus s upon omega p. Okay, a naught upon s. So if I put this value, if I put this value as is equal to a naught upon s upon omega p, so this value will be 1 by f into a naught upon 1 plus s upon omega p times f upon 1 plus a naught upon 1 plus s upon omega p times f. Okay, if I take a omega p as a LCM, so 1 by f, just a naught upon s plus omega p whole divided by s plus omega p times a naught f upon s plus omega p times omega p. Okay. Again, there is the omega. Okay, upon omega. So this term will be cancelled out with this one, so it becomes a v naught upon vi is equal to 1 by f into a naught upon s plus omega p plus a naught. Okay, now again we convert into the this form 1 plus. So what should I do? I just take a common a naught f. I just take a common a naught f. So 1 by f a naught upon a naught f plus, sorry, omega p is also constant. Omega p is also constant. So I take this particular component as a common. Okay, so if I take as a common a naught upon a naught f plus omega p. Okay, so constant term will be 1 plus s upon omega p plus a naught f. Omega p plus a naught f. Now if I compare this term, so now this is the a naught dash upon 1 plus s upon, if I mention this, the omega p dash. Okay, so what is the value of gain? A naught dash. So a naught dash is a naught by f into a naught f plus omega. So this value will be less than a naught by f. Okay, if I say that this is my gain initially, DC gain is this one. If my DC gain is initially this one, now the DC gain is this one. So this DC gain will be less than the a naught f. Any doubt? Why it is less than this one? Because there is some other parameter in the denominator. So when we multiply some other parameter with the denominator, so it will be reduced overall. Okay, and if I compare the omega p dash, so omega p dash, what is the omega p dash? That is the omega p plus a naught. Okay, so basically, if we are talking about the negative feedback, two things will be happen. One, the gain is reduced, and second, bandwidth is okay. Similarly, way if we are talking about the non-ideal op-amp, where this particularly is the cutoff frequency. This omega u is the cutoff frequency. Now, when I apply this operation amplifier in the negative feedback, my cutoff frequency omega u will be increases by this feedback gain factor. Okay, so we discussed this thing. Along with this, what we discussed. Okay. Along with this, we discuss about the Bode plot. So, are you aware about the Bode plot?
Yes, sir.
Okay. So, basically, hello, am I audible?
Yes, sir.
Yes, sir.
Sorry, due to the internet connectivity. Mm, so, in this, along with that one, discuss about the Bode plot, gain bandwidth, input output offset current compensation, op-amp transfer function. Okay. So, two-stage forward amplifier, third order amplifier. Okay, everything will be in this particularly part. So there are, along with that one, the professor discussed some parameters. One is the offset, second is the saturation, that is already discussed, and gain, gain bandwidth. Okay. So what they are saying is that if we have these two terminals with this op amp, we are getting a V out. This is the V1, V2. We generally say this is the VD difference. So V out upon VD. Okay. That is what A naught upon 1 plus S upon omega u. Okay. Now this S omega u is the cutoff frequency.
So screen is not visible.
Yeah, I think now it is visible. Okay. So A naught upon S plus omega u. So this is the operation amplifier V1, V2. We say that the difference voltage VD, output is V naught. So the output upon input ratio is a transfer function, that is A naught upon S plus omega. Okay. Now if we say that this V naught upon VD is okay, A naught upon 1 plus S upon. Now it is a one pole is available. This pole. Okay. Now what is the cutoff frequency of this pole? So how we calculate 1 upon S upon omega u becomes 0. So S is equal to, sorry, I just compare this 1 upon S plus, here is the 1 plus Ts. Okay. So T is equal to 1 upon omega u and F is omega u. So this is the my cutoff frequency. Okay. So if I draw the Bode plot or the gain magnitude curve of this one, so my gain magnitude curve should be like that. Hmm. From the this frequency omega u, it will be start decreasing with the slope of minus 20 dB per decade. Okay, minus 20 dB per decade. How we take the minus 20 dB per decade? Because one pole is available and every pole will be uh, uh, providing the uh, decline of minus 20 dB per decade. Okay. Now, if I say the omega should be greater than omega u, omega should be greater than omega u. So V naught upon Vi, sorry, V naught upon Vd is A naught 1 plus S upon omega u. If I put as A naught 1 plus j omega upon omega u, and if omega is greater than omega u, so omega upon omega u is greater than 1. Okay. So if this component is greater than 1, this component, so can I neglect 1? So V naught upon Vd is nothing but A naught omega u upon j omega. Okay. And if I take the magnitude V naught upon Vd, so it is A naught omega u upon omega. Now with respect to the omega, my gain will be affected. Okay, my gain will be affected. Along with that one, if I say that I have to set the V naught upon Vd magnitude should be equal to 1. Okay, V naught upon Vd should be equal to 1. So, what is the value? So, we can say that if omega is omega naught, a naught omega u, my magnitude response will be 1. Okay, so this is the omega. If omega is omega u a naught, we are getting a magnitude as a 1. Okay, and if I assume a naught is also 1, so omega is nothing but omega u. So if a naught is 1, so I can remove this a naught, and we can say the omega upon at omega is equal to omega u, my gain is 1. And after that, it will be start reducing. It will be start reducing. If I want to check what is the angle of this one, so I can check the angle also. If I want to check at what value of omega this will become 0. Okay, where the magnitude is 0. So we can put this magnitude become 0 and calculate the value of omega. Calculate the value of omega. Is it clear? Yeah. If we use this operation amplifier in a circuit, so as we already discussed, the bandwidth is changed. Bandwidth is okay. Along with that, gain is changed. Okay. If we design a system, gain system with the gain omega u by s with the a, oh sorry, yeah, it is omega u by s. A is equal to omega u by s. Sorry. So when we design a system that is having a gain omega u by s, that is having a resistor value, this is the R2, this is the R1, V naught. So can I calculate the voltage at this point? Okay. So what is the voltage at this point? That is a V naught times the current is what? So first of all, I calculate the current. So if I say this is the I current, so V naught upon R1 plus R2, that is I. And what is the voltage drop at this point is, if I multiply I current with the R1, so we can say the voltage drop across R1. Okay, that is V naught times R1 upon R1 plus R2. Student, wait a minute. Hello. Yes. So if I say that this is the voltage, so that voltage value now the difference between these two is the VD. Okay. So V naught by VD is what? A. That is omega U by S. Okay. Or we can say V naught is equal to omega U by S with multiply with VD. What is the VD? Omega U by S. VD is the difference between these two voltages. We already calculate this voltage VR1. So VD is nothing but V1 minus VR. That is V naught. Okay, so V naught is equal to omega U by S. What is V1? That is simple V1 minus what is VR1? V naught R1 upon R1 plus R2. Can I take this term, V naught term here? So V naught 1 plus R1 upon R1 plus R2 times omega U by S is equal to Vi into omega U by S. Okay, so if I calculate the V naught upon Vi, that is omega U by S upon 1 plus R1 upon R1 plus R2 times omega U by S. Okay, if I divide it by the omega U by S, so it is a V naught upon Vi is equal to 1 upon S omega U plus R1 upon R1 plus R2. Okay. Now if I further classify this one as a, if I take R1 upon R1 plus R2 at the outside, so it becomes a R1 plus R2 by R1 upon 1 plus R1 plus R2 by R1 times S upon omega U and R1 plus R2 by R1 if we define as a RG gain. Okay, so it becomes a RG upon 1 plus RJ times S upon omega. So that is the V naught upon Vi. Okay. Now what is the effect of this one? Initially, if we are talking, so my bandwidth is changed. Okay. What is the gain? So gain, DC gain is nothing but RG. And what is the bandwidth? Overall bandwidth is omega U upon RG. Okay. If we are talking about the 3 dB bandwidth, okay, so when the 3 dB bandwidth is appear, when this term then this term is equal to, okay, this is a 3 dB bandwidth, omega u by r. 3 dB bandwidth. Okay, if I put rg upon 1 plus rg time, if I put s equal to j omega, and in place of omega can I put omega u by rg, so it becomes a rg upon 1 plus j. Okay, rg upon 1 plus j. If I calculate the magnitude, so it becomes a rg upon root of 2. So it shows a 1 upon 2 of the maximum magnitude, 3 dB point. Okay, maximum magnitude 3 dB point. Okay, any doubt?
No, sir.
Along with that, if we go with the magnitude curve, we can draw the magnitude part. Now if we draw the circuit in this way, like for the negative Vi, in the previous case, we are using the non-inverting amplifier where the input signal is applied on the non-inverting terminal. Now in this case, we are using the inverting. Okay, again it is a R1, R2. Okay, this is the Vd, that is the omega u by s, V naught. So V naught upon Vd is nothing but omega u by s. Okay, and this is for non-ideal case. Non-ideal case. If we are talking about the ideal case, so V out upon V1 is minus R2 by R1. Okay. Any doubt in the ideal case? Directly the minus of feedback upon internal resistance, yeah, input resistance, so minus R2 by R1 in the case of ideal. But now in the case of non-ideal, this will be different. It is a V naught upon Vd is equal to omega u by s. Now we calculate the Vd. Okay, so what is the value of Vd? That is the voltage at positive terminal minus voltage at negative terminal. Voltage at negative terminal, that is Vd. Okay. Now Vd is equal to voltage and positive terminal is 0. Why it is? Because it is connected with the 0. And voltage at negative terminal. So this Vd is nothing but minus V negative. Now we are going to calculate the negative voltage. Suppose I assume this voltage is X, Vx. Okay, so can I draw the equation? So the current that is coming from this one, it will be going in this way. So Vi minus Vx upon R1 is equal to Vx minus V out upon R2. Okay, and if I say that, so the Vx by R2 plus Vx by R1 is equal to Vx term I am taking this side, V out term I am taking this side. So V1 by R1 plus V out by R2. Okay, so if I take this is a Vx. So take LCM R1 R2, so it becomes a R1 Vx plus R2 Vx. That is equal to again R1 R2 R2 V1 plus R1 V out. These two cancel out, so Vx is nothing but R2 V1 plus R1 V out upon R1 plus R2. That is Vx. Okay, and what is the Vx? V negative. V negative. Now, if I put this particularly V negative voltage in this VD equation, so what is VD? So VD is minus of R1 V1 plus, sorry, yeah, V in R2 V in plus R1 V out upon R1 plus R2. Okay, this is VD. And if I put the VD in this case, in this equation, so what is V naught? V naught is VD times omega U by S, that is equal to V minus of R2 V in plus R1 V out upon R1 plus R2 times omega U by S. Okay, now we can solve this one to calculate. I think along with this, no,
I have one doubt.
yeah,
This we are assuming that V plus and V minus are not equal, sir.
we are assuming the V plus and V minus is not equal. Why? Because in the ideal op-amp, what we consider that the bandwidth is infinite. Okay, so in this, no current will be passing from that particularly operation amplifier. Okay, so it is only possible that if, like for example, if we say that this is my operation amplifier, okay, this is the V1 terminal, doesn't mean which terminal is this one, this is the V2 terminal. If I say the current is not passing in this through the operation amplifier, that means the difference between these two is zero. Okay, the difference between these two is zero.
So actually here when we are writing this equation, we are assuming the current is not passing, no, sir.
No, we are assuming the current will be passing from that. That's why it is the omega U by S. We multiply the, this particularly is the omega U by S. This is not a non-ideal op-amp. If it is an ideal op-amp, then V naught upon Vi is what? R minus R2 by R1. Why? Because the current will be passing from this one. We calculate this particularly Vx voltage in this term. That means if the current is passing from this one, so what is the Vx voltage? Because we don't know this voltage. Okay, so that's why for calculating the Vx, we use this particular the current passing through this one. But if we write this equation V naught upon Vd is omega U by S, this is only possible when the current passing through the operation amplifier. Otherwise, it is simply that V naught upon Vd is nothing but R minus R2 by R1, because if the current is passing from this one, we already solved this one when current is not passing from the operation amplifier.
Okay, so my main doubt was this that V1 minus Vx by R1
V1 minus,
that V1 minus Vx by R1 is equal to Vx minus V naught by R2.
yeah, we are assuming that the voltage that will be dropping at this point. Okay, we don't know what is the voltage going inside.
Oh, okay, sir.
Okay. If we know this voltage, we can use that voltage also.
So this is more like an approximation.
Yeah, more like approximation.
Okay, sir.
Okay. Now with this, with the help of this equation, V naught is equal to this one. Can I calculate V naught upon Vi? So V naught, there is also V naught term, V out V naught term. Okay. So can I take this term V naught term in this side? So V naught 1 plus R1 upon R1 plus R2 times omega U by S. That is equal to minus of R2 upon R1 plus R2 into omega U by S sin V. Okay. So V naught upon Vi, V in or Vi is nothing but minus R2 upon R1 plus R2 times omega U by S upon 1 plus R1 by R2, R1 plus R2 times omega U by S. But to compare with the standard term is nothing but A naught upon 1 plus S upon omega naught, omega U. But here you can see it is a omega U by S. So what should I do? I just basically represent this one in the way. So I take a common omega U by S from the numerator and denominator, so it becomes a minus R2 upon R1 plus R2 upon S upon omega U plus R1 upon R2 plus R2. Okay. Now the constant term should be 1. So what should I do? I take a R1 upon R1, R2 plus R1, take it as a common. So it becomes a R2 plus R1 upon R1 times S upon omega U plus. Okay. And common as a R1 upon R1 plus R2. In the numerator, it is a R2 upon R1. So these two R will be cancelled out. So it becomes a minus R2 by R1 upon 1 plus S upon omega U into R1 plus R2 by R. Okay. What is the DC gain? Minus R2 by R1. Okay. And bandwidth? This is the bandwidth. This is the bandwidth. So omega U times R1 upon R1 plus R. Okay. And I think professor used some different. Wait a minute.
Sir, your voice is breaking, sir.
Okay. Yeah. So the professor don't that your DC gain is different and the professor DC gain is different and bandwidth is different because professor is using R1 as a R, R1 as a R, and R2 as a KR. Okay, so if we are using the same denotation, so DC gain is minus K, it become positive. Okay, because we are taking the magnitude, so it become a positive, and the bandwidth is omega u upon K plus 1. Okay, so don't be confused with that one. Okay, we are using the R1, R2, and the professor will be using as a R and KR. Okay, any doubt? Now with respect to this one, if I use the simplified circuit is that if I use this resistance V naught, this is my negative terminal, positive terminal, this value is R, this value is R, and this value is Vi. Okay, so my DC gain is what? Now the value of K is 1, so the DC gain is 1, and if bandwidth is omega u by 1 plus 1, so that is omega u by 2. Okay, so if I use this circuit, if I use KR, if I use K times R, so my DC gain is K minus K, and sorry, positive K, and the bandwidth is omega u by K plus 1. Okay, but if I am using only a R term, if I am using only a R term, so in this scenario, the value of K is 1. If I put the value of K is 1, so the DC gain is 1 and the bandwidth is omega u by 2. So if my bandwidth is omega u by 2, my transfer function is what? The transfer function V naught upon Vi, that is 1 upon 1 plus S upon omega u by 2. Why I am taking 1? Because DC gain is 1. DC gain is 1. And why I am taking the omega u by 2? Because the cutoff frequency is omega u by 2. Okay, so it becomes a minus 1 upon 1 plus 2S by omega. Clear? Any doubt? Similarly case that we are using in the when we are applying the positive feedback, yeah, this one. Okay, when we are connecting the Vi as a positive terminal, so we are getting this term. Okay, so if I implement that we are applying on a positive terminal, Vi on the negative terminal, R and R. Now the DC gain value is what? In this scenario, the DC gain is Rg. Okay, and Rg is R1 plus R2 by R1. So the DC gain in this scenario is R1 plus R2 by R1. That becomes R and R upon R. So 2R by R, that is 2. Okay, and bandwidth is what? What is the bandwidth? That is a omega u by RG. Omega u by RG. Okay, and omega u by RG is what? This R1 plus R2 upon R. So that is omega u by 2. Okay, so can you see the difference is that the same circuit, but only the change in the terminal. The plus is grounded, the negative. This is R, this is R, V, I, and V. Okay, now the DC gain is 1. And the bandwidth is omega u by 2. Okay, so the transfer function is 1 upon 1 plus 2s by omega naught, and the transfer function of this one is 2 upon 1 plus 2s by omega. So this is the difference between the when we connect the input voltage with the inverting and non-inverting. Now if the value of resistance R is 1, okay,
The DC gain is -1 or 1, sir?
for the, yes, for this one is the mark. If we are talking about the magnitude, it becomes 1, but it is a minus.
Okay, sir.
Now any doubts?
Sir, please request them to extend the deadline for week 7, sir.
What is the deadline for week 7?
Tomorrow.
Tomorrow. So better that you can send a message to the support team and Victoria ma'am.
Okay, sir.
Okay, because they are only doing that one.
Okay, sir.
If there is some possibilities, because they check all the possibilities, and if it is a possible, so they can extend for 2 or 3 days. But you have to directly mail the support team and Victoria ma'am.
Okay.
Okay. Uh, Furthermore, I think there are lots of things that will be discussed in the week 7. So if the deadline extend, otherwise we will do one more class, extra class for the revision part.
Okay, sir.
Okay. So I think I stop here. Thank you all.
Thank you, sir.
Thank you, sir.
Yeah.